Hey guys, so today I want to go over everything you're going to need so you can build your electric skateboard with the correct materials and to the specs you want. A lot of times I see people oversize one thing on their board, but undersize the others, so they end up just wasting money and material. I am by no means an expert, but I've been into the Escape Love group for a few years now and want to share a few things for those of you who are just starting and to give you a better understanding and a proper direction to go in. So these are the things we're going to cover. The power of your board. Once you have this, everything else will fall into place. Motor size, VESC, batteries, BMS, gearing, and remote. So, the power of your board. This is going to determine everything from the size of your board, the cost and speed and acceleration. I've broken it down into 3 groups: 1000 watts, 2000 watts, and 3500 watts. Of course, there's tons of ratings in between those, but this should at least help you get into the right ballpark. If you're looking for a light board to take you short distances, like on a campus, or you live in an area that's pretty much flat land, and you're trying to keep the cost down, then this will be perfect for you. Now, you have the option to run any of these as a single motor or a dual motor. Personally, I prefer dual motor as it just makes the ride so much better and really helps with not straining any one motor. Especially when you're on the lower end of the watt scale, it really just makes a big difference. Next up, we have the 2000 watt range. I would recommend for most people that they pick something from this category. It's not terribly expensive and you get a lot out of these little guys. They have lots of torque, good for hills, and are heavy rider friendly. Lastly, 3500 plus. These have more power than you're going to need. They can conquer any hill, and they can carry a lot of weight. A couple downsides is that they use a lot of your battery, and because they're quite large, they don't always fit on the same standard truck lengths. One more thing I want to go over is the way they label motors. So they're usually labeled with 2 sets of numbers. For example, at around 1000 watts, you'll see something called 5055, where the 50 is the diameter in millimeters, and the 55 is the length. For the 2000 watt range, you'll see, ones closer to 6354. And for the 3500 watt range, you'll see something like 6374 or 6384, even 63100. And again, the 63 millimeter would be the diameter, and the 100 would be the length of it. Now, by no means is this all of them, but these are some of the more popular options. Along, we're going to be picking our parts to spec out a board together. First step is the motor. Now for the wattage, I personally want a very torquey board, so I'm going to choose a 6384 motor. Now the larger the motor, the more power it's generally going to have. So in this case, it's a fairly large motor. The wattage on the 6384 is 4500 watts, and we will be running a dual motor setup. Next up is the kV. The kV of a motor will tell you the amount of times the motor will rotate per minute per volt. So if you have a 190 kV motor, the motor will turn 190 times a minute for each volt applied. We're going to be selecting a kV a little bit later as it directly affects your speed. Lastly, we have sensors and sensorless. The little connector circled down below on the right is the sensor wires. Ultimately, the hall sensors tell the VESC the positioning of the motor. This will help you with a smooth start from a standstill. It's great for riding super slowly, for rough terrain, and almost a necessity if you're building a mountain board. The only downside is that it's one more thing that can break. As for the sensorless motors, you'll have to kick off a little bit and get the motor spinning before your VESC can take control. If you try to start it from a standstill, your motor will just rotate back and forth and vibrate a little bit. For our board, we will be selecting a sensored motor. Next up, we have our VESC. The biggest piece of advice I can give is to not cheap out. There are tons of cheap VESCs out there that will fail on you mid-ride, which is literally the scariest thing that can happen while on your board. I personally like the Stormcore, U-Box, and Fockbox, but there are many great VESCs you can choose from. For our board, we will be using a Stormcore 60D, which is rated for 12S at 200 amps. Another important thing is to choose the correct amperage. For our scenario, our motors will be drawing 95 amps each, so I need to make sure that my dual VESC can handle at least 95 amps each to the motor if I want to use the full potential of my motors, which I intend on doing. The Stormcore can handle 100 amps each, which is how we get to the 200 amps total, so we will be just fine. The next thing you will choose is the hardware version. The 4.0s are cheaper and can usually handle less amps than the 6.0s, and as well as operate the motor differently, like BLDC mode versus FOC mode. In general, FOC is better of the two, as it's more efficient and a lot quieter, and you also find out that a lot of hardware 4.0s can't run FOC very safely. In our case, we are using hardware 6.0, and we will definitely be running FOC. Next thing to make sure is you get the correct voltage. We will be using a 12S system, as that is the max voltage our vest can handle. I always recommend having higher voltage because the higher your voltage, the less current your system will need to draw, and in turn you will have less heat, which is the biggest waste factor. Lastly, I highly recommend getting one with a Bluetooth module or getting a Bluetooth module installed. It will help you so much throughout the life of your board, as you can see what's going on with your board on your phone as you ride it, versus the alternative of bringing it home and plugging it into your computer if you want to know anything about what's going on. Super helpful with troubleshooting. One last point on this topic I want to make sure that I mention is that the max amp rating on your vest is for your motor current max, not the battery current max. You will see what I'm talking about when you eventually get to programming your board. Ubox even tells you this on their website, but many people still program their boards to sometimes have a higher amperage on the motor current side than their vest can handle. Now we have batteries. This is the place where people usually undersize things. They will have two motors rated at 70 amps each, but they'll have a battery pack that can only output 60 amps total. They are definitely not getting the most out of their motors and have overspent on that end of it. Now I'm going to show you how you can find out the capacity of your batteries, which is measured in milliamp hours, as well as the output current that they will be capable of, which is measured in amps. Now the two most popular types are lithium polymer and lithium ion. The difference between the two is that LiPos can output more amps, are generally cheaper, and can last about 200 charges, or about 2 years. Lithium ion are more expensive, don't have the same output capacity, but can last a lot longer, about 300 to 800 cycles, depending on how you care for them, which is about 3 to 6 years. So we'll start with LiPo to see how many amps a pack can output. You would firstly take the milliamp hour of the battery, multiply it by the C rating. Make sure you choose the constant C rating and not the burst if you have one on there. And then you divide it by 1000. Then you take that number and multiply it by the amount of packs you have in parallel. That will be your total rated output in amps. And don't worry, I will go over an example shortly. For lithium ion, it's a lot easier. You simply look up the specs and it will tell you the output in amps for each cell. Multiply that by however many cells you have in parallel, and that's it. One more thing I want to mention about LiPos is that they are a lot easier to cause fire than a lithium ion because they're softer, their chemistry is a little bit unbalanced, so if you overcharge them, undercharge them, too cold, too hot, many different things, puncture them, they have the potential to cause a fire. So along with all the other points that I made about these batteries, that is the biggest downside of LiPo, so you have to make sure that you care for them really, really well. I actually like to keep them between 3.4 volts and 4.1 volts. I would get less range, but ultimately a safer battery and just generally safer. So here we have a Turnigy LiPo and a Molicel P42A lithium ion. These are the more popular batteries in their respective chemistries. Now for the LiPo, you can see that our capacity is 5000 milliamp hours. Our constant C rating, which will be the smaller of the two, is 40C. We multiply 40 by 5000 and then divide the whole thing by 1000, and we get 200 amps. Now with LiPos especially, manufacturers seem to get carried away with their outputs, so realistically, this battery will only output about 100 to 150 amps tops. Now as you remember, our motors are rated for 95 amps each, which will put us in the ballpark of about 200 amps. So by that logic, if I take the conservative number of 100 amps per pack and I multiply it by 2, I will safely get 200 amps out of the pack. So that means I would need at least 2 packs in parallel. As for the lithium ion, it's rated for 45 amps, which could probably get us about 35 to 40 amps so that you don't kill your battery's life cycle really quickly. Now I would take the 200 amps of my motors, divided by 35 amps of my battery, and I'm left with 5.71, which means I would need 6 batteries in parallel to meet my motor's ratings. Now I could get away with less output on these batteries, probably, but I like to rate everything accordingly so that I get the most life and the most enjoyability out of my setup. As long as you don't over-discharge or overcharge your batteries, they'll live plenty long if you rate them this way. Now a quick point I'd like to make is the voltage levels of the batteries. 3.7 is the nominal voltage level of each cell, with a LiPo or lithium ion. It's basically the halfway point from full charge and fully discharged. And it's the level you want them if you decide to store them for a few months. One other thing I want to mention is the thickness of the batteries. The thickness is going to determine how thick your case is going to be, which is why for the lithium ion, I have about 1 inch, so I know that they're relatively thin. The LiPos is where it starts to get a little bit finicky. I chose a 3S LiPo because it's 1.25 inches thick. If I go 4S or 6S, that's when they start to get a little bit thicker, and you're better off mounting those on the top as like a mountain board. But since we're not doing that, I gotta be more cautious. So I chose a 3S, which is only about 1.25 inches thick. Next thing I want to go over is the battery capacity, as this will determine our range. The rule of thumb is about 10 to 15 watt hours per mile for a street board, and about 15 to 30 watt hours per mile for an all-terrain board. So you'd want to build your board to fit where you will be riding. I'm going to do a little bit of trails and hiking paths with mine, so I'm going to play it safe and just use the 30 watt hour per mile figure. I would also like about 15 miles of range, as that's about how far the round trips are on a few of the paths I like to take. So I'll simply take my 15 miles, multiply with my watt hour figure, then take that number, which is 450 watt hours in this case, and divide it with my nominal voltage levels. Since we chose 12S, it'll be 44.4 volts. So far we have taken 15 miles, multiplied by 30 watt hours, which gives us 450 watt hours. Divide that by 44.4 volts, and that'll bring us to 10 amp hours. I multiply that by 1,000, since batteries are rated in milliamp hours, and I'm left with 10,000 milliamp hours. Now I want to go over quickly how you would wire these packs. Now, as we said before, we are looking for a 10,000 milliamp hour system. Now if I divide that by 5,000 milliamp hours, that means I'm going to be left with 2 batteries in parallel. So we've decided that we're going to go with LiPo, since it's most cost effective in the short run and much more power output for a smaller size. So that would mean I would have 4 batteries in series, because my system is going to be 44.4 volts and a 3S battery is going to be 11.1 volts each, which would leave me with 4 batteries in series. So that would mean I would have a 12S, which is 12 cells in series, and 2P, because I have 2 packs in parallel. So ultimately, when you put them together, they're going to look like this. Now, once you put them in series, it's almost like you're creating your own little pack. So even though these are 4 Turnigy LiPos, I'm like creating my own little pack here. So this guy is going to be a 12S 5,000 milliamp hour pack. Now to wire it, I would take each individual cell. Now this would be almost identical to lithium ion as well. So I'll take each Turnigy pack. So this is my 1, 2, 3, and 4. So it's 4 packs that I purchased that are rated at 3S each. They each are going to have a black and red wire. So what I would do is I would take my positive end, my negative end. At my negative end. I would jump my negative end of one battery to the positive end of the other battery. Then I would take the negative end of that battery and move it over to the positive of the other battery. And basically, you're just going to be going in and out all the way throughout the whole thing. So by the end of it, if I take a meter, my multimeter, and I put one lead here, and I put the other lead all the way over here, it's going to read 44.4 volts if they're charged to 11.1 volts each. Now that I've got them in series and I've got the 12S portion, I need to get the 10,000 milliamp hour portion. So now I need 2 of these guys in parallel. So what I would do is I would simply take the main leg of the pack that I just created, which in this case is right here. I would take this guy. I need to jump him with the identical pack that I create over here. And I'll put a little moret. I apologize for the drawings here. I would do the same with my negative. So I would take the main leg of my negative, which is here, with the main leg of my other negative, which is right here. Basically, bring them along, following this black line that I already have drawn here, all the way to the VESC. So now, at the VESC, right here, I'm going to have 12S, 44.4 volts, and 10,000 milliamp hours, which is what I wanted. So if I take my multimeter again, and I put my leads one here, and one here, I'm going to be reading 44.4 volts. Moving on to the BMS. So what does it do? As you charge your batteries, some of the cells don't charge evenly. It results in overcharge and over-discharge. It will ruin your batteries quickly and cause fires if left to get bad enough. That's where the BMS comes into play. It makes sure that as you are charging or discharging, that they do so evenly and you don't have one cell that's much higher or lower than the others. Let's take a look at an example. So let's say I have a 2S system, just for this example, and these are my two cells. Now this is going to be my threshold. This is my 3-volt threshold line. That is the lowest I want any cell to ever be. And I have another one here. Now let's say I charge these batteries, and for whatever reason, this one ends up charging to 3.8 volts. And this one charges to 3.4 volts because of an improper balance. Now as they deplete and they both go down, this one will reach 3 volts a lot sooner. The problem is it'll continue to deplete because the battery pack as a whole might still not be below the voltage requirements that the VESC is set to. So maybe your VESC is set to continue working as long as it sees, more than 38 volts as a whole. Accumulatively, your battery pack might be above this value, but if you have one cell that's going below 3, that's where your problems start to happen, and that's where damages start to occur. And that's why it's so important to use a BMS. Now there's two ways you can wire a BMS: for charging and for discharging, and for charging only. Best case scenario, you set up to do both. Your batteries will last much longer, and it'll protect you against any short circuits. Unfortunately, at the time, it can be difficult to find one that can output more than 120 amps or higher that is a reasonable size. Now, using it for charging only has its ups and downs as well. It's harder to maintain your battery life as you only monitor the cells when they charge. To be safer, you need to put a fuse. Due to poor connections by the user, or a product could potentially cause a fire, could potentially cause a short, and that could cause a fire due to the overdraw of the batteries. On the plus side, you'll pretty much have an uncapped power output, since there's nothing intervening the discharge. So at the end of the day, you can decide which option is right for you. Whatever direction you decide to go, I highly recommend getting one with Bluetooth connectivity. The odds that you will ever open the pack to make sure that each of the cells is balanced on a routinely basis are next to none. At least this way you can easily check the life of your pack and make sure it's within the correct parameters as to not cause damage to anything. Okay, so now I'm going to show you how to wire the BMS. It may look intimidating at first, but it's a lot easier than it seems. So you're going to have one lead more than the amount of cells that you have. So in this case, we have a 12S system, so we're going to have 13 leads. The first lead is usually going to be color identified as black. That is going to go to the negative of the first cell. So in this case, we have 1 to 1. Your last lead is going to go to the positive end of your last cell. All the other leads are going to go to the positive of the adjacent end. So in this case, we have 1, and we're going to have 2 right next to it. It's important to make sure that you get this order correct, because if I end up putting 2 somewhere over here, at another positive terminal, it'll mess up everything. Basically, the way this thing reads it is pretend that you have a little meter here in between each one of these, and it's basically just taking the voltage readings from this end to this end. And it does that across all 12 cells, and it basically starts to judge which ones need more voltage, less voltage, just discharges them into a capacitor and recharges another cell accordingly, so that you're not wasting any energy. Now this is what it would basically look like if you're doing a lithium ion setup, if you consider each one of these one cell. As for a LiPo pack, you're going to see something like this. Each cell is going to have its own little wire as labeled here, and you're basically just going to be connecting the leads over here to the wires over here. Each one of these, again, basically just goes to the positive end of one of the cells. So this would be almost your, the black wire that we have over here. So that's your first one, and this one's gonna, take us to the positive of one of the end of the cell. This one is going to take us to the positive of the other end of the cell, and so forth. And you're just going to continue that across all your packs in the similar fashion that we have here. So again, we have 2 to 2, we have 3 to 3, 4 to 4, and and so forth. Now, when it comes to, again, this is just a 12S, let's say 1P. When it comes to a 12S 3P or 4P, you'd basically just double them up. So instead of having one cell here, you're just going to end up, you're going to pretend you have a second cell there, and this wire over here is going to be connected to the positive end of both those cells. And you're basically just lining them up on top of each other. So if I had this whole setup drawn again right below me, somewhere over here, I would just overlay it on top of that and combine the wires accordingly. They're all going to be basically in parallel, because it's going to be reading the accumulated voltage of the 2 cells or 3 cells or whatever it is in parallel. And that's pretty much it. Okay, so next up we have the gearing. Now this is going to determine how fast you're going to go, how fast you're going to accelerate. It's going to affect your battery life. This is pretty much everything. Now, to make it easy, luckily we have a gentleman that made a great website. I'm going to leave the link right up here. I use this thing every single time I end up building a board. Let's just kind of go through the parameters that we are allowed to have. So we have battery type, pretty straightforward. Number of cells. Now, the higher the voltage, the higher the speeds. Like we said, for the motor KV, every volt is going to give us this many rotations. So 1 volt will give us 190. 44.4 volts will give us 44.4 times 190. Efficiency, I honestly don't really touch that. Motor pulley teeth. Now this is kind of motor pulley and wheel pulley. This is kind of where I go to wherever I'm going to be purchasing my stuff and taking a look at what they have. I tend to like to try to stick to a 4-to-1 just because I like mine super torquey. I don't want them to struggle at all with going up any hills or bumps or anything like that. So in this case, they have 15 and 36. To get your gear ratio, you basically just divide them, and that'll tell you what it is. Wheel size: bigger wheel, higher speed, slower acceleration. So you gotta kind of take that into consideration as well. And basically, what this is gonna do, it's gonna take everything that we have listed here, and it's gonna give you a top speed. Now, with this top speed, again, the higher it is, the less acceleration you're gonna have. So you kind of just got to be the judge of that. And yeah, then we're going to go through one example for our own board that we're going to be building, so we can get an idea of what we're looking at. So here we have our build. So like we said, we have LiPo. We're going to use a 12S system, which is 44.4 volts. I've decided to go with a 140 kV motor. I've already played around with this, and I've seen the speeds that I'm going to get, and I've decided to go with a 140 kV motor, as that is pretty much as fast as, I'm going to go with the weighted, but that's pretty much as fast as I'm willing to go or need to go, and I'd rather reserve as much as I can for the torque. If we move on, so our motor pulley teeth is going to be 15, 60 for the wheel. Again, like we said, 60 divide 15 is going to give us our 4-to-1 ratio. Our wheels are 190 millimeters in size, which is equivalent to 7.5 inches. And it's going to give us our speeds of, I'm going to go off of weighted, of 47.31 kilometers an hour, which is more than I'm going to need. Now our ERPM, now basically how you get this number is you would just take your KV, so in this case 140, multiply it by 7, which is your 7 pole pairs, which is how many pole pairs my motors have, and multiply that by your voltage, which is 44.4 volts. Now one quick thing I want to mention, I forgot to mention earlier, if you have a hardware VESC of 4.0, you need to make sure you do not exceed 60,000 ERPM. This number cannot be more than 60,000 ERPM. It can, but you need to make sure that you set it in the parameters of your VESC for it to be 55,000. Because your DRV will blow, and many people's has blown, especially if you're running a 12S setup, and it's going to throw you right off the board. So you got to make sure that you do not forget this if you decide to go with a hardware 4.0. The 6s, I believe, can go up to 150,000, so we are nowhere near that limit. But yeah, that's just something to keep in mind. Okay, nearing the end, we're on to the remote. Now this one is pretty straightforward, just buy a good one. The first one I purchased, I really wasn't aware of the quality of remotes, and when I went downtown and there was a lot of different signals, I guess, going around, I lost the signal to my board a bunch of times, to the point where I was actually uncomfortable to even ride it at all down there. It would even happen sometimes in the city near where I live. You know, when I pass satellites and stuff like that, it would just seem to just completely botch the whole thing, and I would accelerate and decelerate, and it was just a mess. So get a reliable remote and get one that's gonna keep connection no matter what. In our case, we're gonna use one called Hoyt, which is basically the remote you would probably use if you went to New York. Just because of how dense it is, this is the remote that you'd want for there. That's how reliable it's been been tested to be. Okay, and that's pretty much it. Once you have all these components and you put it together, you're gonna have all the specs for your board, and hopefully it's gonna be designed the way you'd like at the end of it when you start riding it. Now let's take a quick look and a recap of everything we have. So we have dual 6384 motors rated at 9,000 watts, our Stormcore 60D, Turnigy 12S 10,000 milliamp hours, rated for 400 amps of discharge, which again we're probably closer to the 200 amp range. Our Hoyt Puck 12S BMS. Now I've installed this so it's charge only because I couldn't find one that I could fit in there that was rated for 200 amps, and I was just super cautious with everything that I did and made sure that there's nothing that can come loose. All my solders were perfect, and I would heat shrink and then insulate it with rubber tape right after. And we have our wheels at 7.5 inches, our gearing, which is at 60 teeth for the wheel and 15 for the pulley. Now I've already ridden this thing and it is amazing. It is super torquey, just like we thought. I've got up to 45 kilometers an hour. I probably could go a little bit faster, but that's kind of where I get a little bit uncomfortable. And yeah, the range seems to be in the same ballpark that we were looking at. I get between actually 15 miles is pretty much what I get. And yeah, just being able to use the Bluetooth for the BMS, being able to use the Bluetooth for my Stormcore has been a huge help in everything. So hopefully this helped you guys. I wish you luck on building your own board. If this did help you at all, please consider subscribing and throwing a like. And yeah, I'll see you in the next one.